Alright guys, welcome to the Earth Science Semester 2 Final Exam Review with Mosel and Germ. We're going to get started here. Kind of lead you through each question, help you out, so your review goes pretty smooth for you guys. So here we go. Looking at this picture, this is question 1A on your review. If you remember the Slinky lab we did, it was so awesome. We were looking at P waves and S waves. So in this diagram, A in that diagram represents a P wave where it just moves straight across. B represents an S wave which moves side to side. So A is a P wave, B is the S wave. Alright guys, this is for question 1B, and it'll help you with 2E also. Right here we're looking at our waves. We're looking at primary waves, secondary waves, and surface waves. So number 1 here in this graph would be, we call your primary. Number 2 is your secondary. And number 3 would be our surface waves. So also, I'm doing this in the Sox. This is a home run. Awesome. So let's get back to the review. Primary, those come first. Remember, those are the fastest. And our secondary come after our primary. And then come our surface waves, which do the most damage. All right, for 1C on your review, we're looking at our P wave and our S wave. And we're trying to determine what's the difference in arrival time. So we're looking at our 2 times here. So we're just looking for the difference. So it's pretty easy math there. So looking at the difference in time, that's going to be 1 hour, 3 minutes. So that's how much longer that S wave arrived after the P wave. So we're looking at the arrival times here. And this is going to get into looking for the epicenter of the earthquake. So again, this is for question 1C. Right, for question 1D and 2A, we're kind of looking at the lag time here, the travel time. So we're looking at the difference between the P and S waves and how fast they went in 1 minute, their travel time for 1 minute. So on this one, you would have to take out a note card and drag it on your chart here. So you want to kind of find out with your S and P are at 1 minute and somewhere right in here. And that would give you your epicenter distance. Okay, remember that it's 10 to the third kilometers. So again, you would have to take your note card. I'm sure you'll have one in class. You'll have to use that to help you with this question. And when you take the final exam, you also have a note card to help you with your chart. Here for question 2B and C, what you're looking at are, we're trying to figure out the epicenter and which city is closest to the epicenter. So usually when we're talking about epicenter, and when we draw our circles after finding our P and S wave lag times, we see where our circles intersected. So on this one, kind of see all 3 intersected right around here. So our city that would be closest to the epicenter would be... you probably said Chicago. You're wrong. It would be Panama City because it is closest to our 3 circles intersect. So that's your answer for 2B, and that also help you with 2C. All right, for question 3. Usually when an earthquake hits, the damage is going to be the result of broken gas lines. And you see this picture here. This was in Japan. So you see fire, 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 fire. So a lot of fire, and that fire is caused by broken gas lines because when the earth shifts, those lines break underneath the ground and releasing gas, and that gas, once it is ignited, starts massive fires. So that's one of the major damages caused by earthquakes. All right, for question 4, we've talked about the San Andreas Fault. You guys also watched that awesome movie in class, which was all about the San Andreas Fault. So if you forgot where the San Andreas Fault is located, it's located right here in Cali, California. All right, so remember it affects it goes down pretty much the coast line here. Kind of comes inside here as it moves down towards San Diego and Los Angeles, and it kind of runs right through San Francisco. So this, remember, San Andreas Fault, transform boundary type of fault, and that runs through California. All right, for the question number 5, I know it looks like a big diagram with all the different layers of the Earth, but the one we just pretty want you to know for the final is A here, and as you can see, A is right underneath the ocean. So A would be the oceanic crust. So you don't really have to know for this question the mantle, the inner core, the outer core. This one you pretty much just have to know where the oceanic crust is in this diagram. There's a lot on this page. It's a lot to get through, so I think you guys will do good. So first we're going to look over here at our picture here. It says transform boundary. We just talked about one of these transform boundaries in a couple questions right before this. So the San Andreas Fault is a transform boundary. Okay? And a transform boundary doesn't move, it doesn't pull apart or come together like our divergent and convergent. It kind of moves side to side. Okay, that's a lot there, so I'm going to erase a lot of that for you guys. So again, a transform boundary, San Andreas Fault is a form of that, and this is a lot of erasing to do. Taking a long time here, so sorry. But again, a transform boundary moves side to side, and a most famous transform boundary is the San Andreas Fault. Okay, moving on to our picture over here to the right. This would be an example of a divergent boundary. And in a divergent boundary, we get a subduction zone. That is where one piece of the crust moves underneath the other piece of crust. So in this instance, it's the oceanic crust moving underneath the continental crust. Okay, so this is divergent. Divergent means to come together. Down here, our last picture, this would be a convergent boundary. Convergent, we move apart. And in a convergence, we have our melting, we have our magma down here coming up, and as it comes up, new crust is formed. So new crust is more in the middle, and the older crust is out to the sides. So hopefully you got all that. I know that was a lot, so if you have to rewind and go back, please do so. I know I wrote a lot there. It's a little messy, but I do apologize. All right, here. So like I was talking about on the last slide, here's some examples. So a famous transform boundary that we know about, that we hear a lot about, is the San Andreas Fault. Over here, a form of a divergent boundary that occurs is over in Middle East, and the Red Sea is a version of that. So the Red Sea was not always here. What happened was the Arabian Peninsula and in Egypt started to pull apart because they're set on a divergent boundary, and when that divergent boundary started to pull apart, water filled in, creating the Red Sea. Down here, we have an example of convergent boundary. We have our Indian subcontinent, so that's where India is, hidden our Eurasian plates, and as those two plates collide with each other, we have the Himalaya Mountains forming in the middle, where those two plates are converging on each other. All right, for this question, I believe we're looking at here, we have our oceanic plate and our continental plate. So when those plates converge on each other, what we have are volcanoes forming. So as the oceanic plate submerges, the asthenosphere and the magma comes up, and it pushes the continental plate up, and also pushes that magma up, which gives us our volcano ranges that form. All right, for question 6G, we're talking about our P waves. So, as P waves travel through the Earth, they travel through everything. So, they move through everything, but once they hit the inner core, those P waves are deflected. So, they go off in different directions. Okay, so for that question, you just got to know P waves do travel through the different layers of the Earth, but once they hit the inner core, they are deflected in all different directions. All right, in this diagram, we have a lot going on here. So up here in the corner, you have a mid-oceanic ridge forming at a convergent boundary. And as that mid-oceanic ridge is formed, remember the newest soil, newest rock is located near the ridge. And as you go further out from the ridge, the age increases. Over here, as we have an ocean plate converging with a continental plate, a trench is formed. Okay, so that's where two plates converge. And underneath here, we have our convection currents in our mantle. Remember, warm rises, colder rock sinks. Okay, so we have our current constantly moving those plates. Over here in our larger picture, you kind of can see here where the magma is coming up at a mid-oceanic ridge here, and the land is moving out. So remember, the age increases as you move away from the middle of the ridge. Aloha. So, how were the Hawaiian Islands formed? So, pretty much the Hawaiian Islands were formed from a hotspot. And pretty much what a hotspot is, it's a plume of magma that punches up through the crusts. And as the plates move, that plume will break through spots in the crust, forming islands, hence the Hawaiian Islands. So we have Hawaii, Maui, Oahu, and Kauai. So each island was formed from a hotspot as the land moved over it. So as they moved over the hotspot, each island was created. So you kind of could see that over here in this picture. We have our second island there being created. So as that plate shifts and moves over that hotspot, a new island was formed, and that's our third island there. That would be Maui, if we're looking at our islands in succession. So again, just remember the Hawaiian Islands are formed from a hotspot as that magma punches through the crust, pushes holes through the crust. We're going back here now to like the start of the semester, like way back to like February and January. So these were our three types of volcanoes. So I'm sure most of you have forgot these types. Hopefully you haven't, but we'll cover them here. So right here, our big daddy right here, those would be our composite volcanoes. Over here, we have everybody's favorite, the cinder cone. You see how it has the cone shape at the top. And down here, the ones we find in Hawaii would be our shield volcanoes. Question number 10. Viscosity and pyroclastic material are no longer on the exam. Alright, looking at this map of the United States of America, we have our legend over there, a triangle for our Raleigh, North Carolina, the star for Minneapolis, Minnesota, and the circle for Phoenix, Arizona. So looking at this map, this goes back to our locations on how it affects our weather and our temperatures. So looking at this map, which these cities would be located close to a large body of water? So that's what you want to look at. So it's Raleigh, Minneapolis, and Phoenix. So if you're looking at this over here, we have the Atlantic Ocean. And our triangle, which is Raleigh, North Carolina, is actually the closest to a body of water. So remember, when a city is located close to a body of water, its temperature is regulated where it doesn't really get too high, it really doesn't get too low. It kind of stays consistent throughout the entire year. So a city like Raleigh, North Carolina would have pretty much a consistent temperature, wouldn't get too high, wouldn't get too low, unlike cities like Minneapolis and Phoenix. In Minneapolis, it gets really warm in summer, it gets really cold in the winter. It's not near a large body of water. Similar to Phoenix, where Phoenix kind of stays really, really hot, but it also does cool off a lot at nighttime. People really don't realize that. So hopefully that helps you with these questions. And just looking at the latitude of these cities also, you have Minneapolis is at a higher latitude than both Phoenix and Raleigh, and that would affect the type of weather it had. The higher your latitude, most likely the colder your temperature because of the amount of sunlight you receive throughout the year. All right, here we're talking about a dew point, not Mountain Dew, but the dew point. The dew point is the temperature at which the air would have to cool to form clouds. Okay, so we're talking about the dew point. Also, we're talking about relative humidity down here. And relative humidity is the amount of water air can hold at certain temperatures. Okay, so at certain temperatures determine how much water the air can hold, and we call that relative humidity. So if it's 10 degrees Celsius, water vapor would be 100% relative humidity. However, if it's 20 degrees Celsius, it would be 53% relative humidity, and 30 degrees Celsius, which is even warmer, 28% relative humidity. So this, remember, relative humidity is the amount of water that air can hold. And White Sox just got another hit. Yeah, baby. All right, looking at this question. This goes back to our lab when we did soil versus water. And if you could see here in this graph, right here, this is our soil. It's the temperature of soil versus and water versus time. And down here is our water. So as you can see, water kind of stays consistent. Doesn't really get too hot. It kind of keeps the same temperature. Goes up just a little bit, unlike soil, which is cool, warms up, and cools down. So what you want to remember for this, land heats up faster and also cools down faster than water. All right, right here we have four different type of cloud types. Remember our clouds. So we have our names for them. So over here, our Latin name for these types of clouds, kind of wispy, are your cirrus clouds. Right here we have our ever famous cumulus clouds, nice and fluffy heaps. Over here we have our stratus clouds, usually represent rain is coming. And also here we have our fun cumulo, I'm probably going to spell it wrong, nimbus clouds. And those are associated with low pressure systems and usually mean that it is going to rain and there's going to be thunderstorms. I don't even know if I can make a lightning bolt. Can I make a lightning bolt? Oh, kind of, sort of. It looks like a tooth. I don't like that one. All right, so these are associated with lightning, thunderstorms. There we go. That's a little bit better. Alrighty, so those are four different types of clouds: cirrus, cumulus, cumulonimbus, and stratus. Alright, we have a lot going on here in question number 19. So first, right over here, so when air meets a mountain range, we have our warm, moist rising air rises up, creating rain coming down the other side, dry descending air. This is called orographic lifting. So orographic lifting, I'll spell it for you. O-R-O, graphic lifting. So this is what happens when air runs into a mountain range where it rains on one side and on another side it is dry, creating what we call, remember, a rain-shadowed desert. Down here is frontal wedging, and not a wedgie, wedging. So I hear all the giggles out there. So pretty much with frontal wedging, the warm air rises over the top of the cold air, and as that happens, the warm air eventually will replace that cold air. So what you want to remember is the warm air is moving over the cold air and eventually will replace the colder air. And this is an example of a warm front right here. And in this picture, we have two cooler air systems colliding, and they're converging on each other. And as they converge, that low pressure goes up, creating warmer air. So as those two low pressures come in, they create a low pressure system. And when that happens, clouds usually do form. All right, guys, so this should be pretty easy. We've talked a lot about this greenhouse effect. Remember, greenhouse effect is when that sunlight comes from the earth. Some of it is reflected, and some of it becomes heat, and some of it is reflected back into space way out here. Yay, out to our aliens. I can't even draw. Let me see, can I draw like a little alien ship? Kind of, sort of. So back into space. But a lot of it is trapped inside our atmosphere and by the carbon dioxide and other gases, and that helps keep the Earth warm. Also, remember, some of the sun's rays are reflected back off the clouds, especially during the daytime, and that's why underneath here is cool during the day from the clouds. It doesn't allow that sunlight to reach the surface to heat us up. But it's different at nighttime because the clouds actually act as insulation for our planet. So that outgoing radiation trying to escape back into space can't really escape because it's absorbed and reflected by the clouds. So it comes back down and keeps us warmer at night. So in the wintertime on a cloudy night, you won't see that ice forming on your windshields in the morning, unlike clear nights in the wintertime where that radiation does go back into space in our atmosphere, and our planet is not insulated, so it is colder at night. So again, what you want to remember, at nighttime, clouds keep it warm. During the daytime, clouds cool down the Earth. All right, this is super duper easy. Weather versus climate. Who will win? My money is on climate. But what you want to know is the difference between weather and climate, and primarily climate. So just remember, climate is like the average conditions in an area at specific place. So like the average conditions. So where we live in Chicago, usually we have nice warm summers, and our winters are relatively cold. That would be climate. Weather, on the other hand, is the conditions at a point in time. Like our weather today, if we're talking about Friday, is going to be in the 80s and sunny. That would be the weather for a specific point in time. Usually it's not 80 in May, but today it is. So that is our weather, specific place and time. So again, remember, weather, specific point, climate is the average conditions. All right, pretty easy concept here. Here's a high pressure. So remember, high pressure, when you have a lot of pressure, it's being pushed down, and for a high pressure, it's moving in a clockwise direction, the wind direction. Just opposite, low pressure, it's not being pushed down. The air is allowed to come up. Kind of remember when we were pushing down in a balloon for the high pressure, when we released, the air came up. So when you do that in a low pressure, that air is moving towards the center. Okay, so what you pretty want to know, high pressure pushing down, and low pressure, that air is going to go up. And that low pressure is going to allow storms to form. All right, guys, question number 24. We're looking at the different air masses that affect our weather here in the United States. Remember, we're located right there. Can you see it? I put too low dots. I put a lot. So we're right in there, okay? So that's the Midwest. So what two types of air masses could affect our weather here in the Midwest? Well, the ones we really don't like is our CP, which is our continental polar. That brings in that cold air, which we had the last couple weeks around here, which we don't like. But the ones we do like, which brings in that nice warm, sometimes moist air, the rainy, when we get a lot of rain around here, would be our maritime tropical coming down here from the Gulf of Mexico, bringing us that nice warm air from the Gulf of Mexico. So you want to know those are two air masses that affect our weather here in the Midwest. All right, here we have our symbols for our different types of fronts. So right here, we have our cold front. 2 would be our warm front. Right here, this would be our stationary front. Our stationary fronts don't like to move, and a lot of times if they're bringing us bad weather, we don't like them because we get that bad weather for long periods of time. And right here, this would be an example of an occluded. See if I can fit this in here. Can I do it? Occluded. Probably not. Occluded front. So those are your 4 types of front. Ian, the umpire in the Sox game, just made a bad call. But those are your types of fronts. Anyways, we'll move on to the next question. Last question here that we're going to cover. This one's talking about the global conveyor belt, and we're talking about the salinity of the ocean water. So remember, as we go towards the poles up here, so the North Pole, as you go down here towards the South Pole, the water has higher salinity and sinks to the bottom of the oceans. Reason for that is because these are colder regions of the ocean, and when ice forms, there's higher amounts of salts, so they have higher salinity levels in the actual water because most of the water in those regions is frozen. So remember that near the poles, because of the water freezing, there are higher salinity amounts in the ocean water near the poles.
They look hilarious.
Hilarious!
Look at Noah.
Stop!
No.
You're doing a good job there, Anya. One more time.
Seniors, it was so much fun making this review for you guys. It made me cry. Good luck, guys. Take care and good luck.